In the last lecture, we worked out several examples illustrating the application of the Laplace transform technique to the solution of transients in networks. We also made a special mention of the particular virtues that Laplace transform technique brings to the solution of such problems. We compared the Laplace transform method with the differential equation approach and pointed out the various benefits, benefits that the Laplace transform technique will bring in. We also made a note that where the initial conditions are specified at different points of time, not necessarily all at t equals 0, the differential equation approach will be probably more beneficial than the Laplace transform technique, because there is no provision in the Laplace transform technique to take care of specification of conditions at different points of time. If you have such a situation, then you once again end up in arbitrary constants even with the Laplace transform solution, so there is no special advantage in that. Today we will start with another example of a network transient problem in which a discontinuous source is present, and then later on we move to a discussion of the application of the Laplace transform technique to a general system. So let this be a voltage source Vs included in a circuit of this type, a capacitance of 2 farads and a DC source of 4 volts. And this Vs is a discontinuous source having 1 volt, a pulse lasting from 0 to 1 second. And we will also assume that steady conditions are reached at t equals 0 minus with Vs equals 0. So before the pulse is switched on, Vs is of course 0, and at that time we assume that the steady state conditions are reached. The question that is asked is find Vct for t greater than or equal to 0. This is the question that is asked. Now we set up the transform diagram for this. Before doing that, we need to know, because there is one reactive element, the capacitor, we should like to know the 0 minus value of the capacitor voltage. So to do that, let us see the system, the various parameters in the system at various variables in the system at t equals 0 minus. At t equals 0 minus, this voltage source is 0. You have a 1 ohm resistance, a capacitor, another 1 ohm resistance, and a DC source. This is 4 volts, this is 1 ohm, this is 1 ohm, and this is a capacitor of 2 farads. So obviously, if the steady state conditions have been reached in the circuit, this 4 volts will drive a current of 2 amperes through the 2 1 ohm resistors in series, and there will be a 2 volts developed across the capacitor. Therefore, Vc0 minus is 2 volts. So that is the voltage initial condition of the capacitor that we have to use in solving this problem. So let us form the transform diagram of this. Transform diagram of this would be, for the voltage source, you have the Laplace transform of this voltage source. This is ut minus u of t minus 1 is a pulse function. Therefore, the Laplace transform of this will be 1 by s times 1 minus e to the power of minus s. That is the voltage source. In addition, we have this resistance, another resistance 1 ohm, and then a capacitance whose impedance is generalized impedance is 1 over 2s, and then a source representing the initial capacitor voltage. This is a 2 volt source, therefore this will be 2 upon s, and then you have the Laplace transform of this DC voltage source, which is 4 upon S. Now the capacitor voltage is what is required. So it is the voltage across these two nodes. This is Vc of S. As pointed out in the last lecture, when you are interested in finding the capacitor voltage, you should not try to measure the capacitor voltage across this portion only, because it is the totality of these two together is what represents this 2 farad capacitor, including the initial condition source. So when you want the capacitor voltage, it is the voltage between these 2 points which has to be calculated. Now a simple way of solving for this would be to take the node equation approach, take this as the datum node and call this 1, this as 2, this as the 3, and perhaps this as 4, and therefore if you find out the voltage of node 1, that will yield you the capacitor voltage, which is the voltage of course with reference to the datum node, node 1 with reference to the datum node. So writing the node equation at node 1, Vc of S times the sum of the admittances connected to this node, 1 plus 1 plus 2s minus the coupling terms with reference to the voltages of the other nodes. So with reference to node 2, we have 1 by S times 1 minus e to the power of minus S. That is the voltage of node 2, and the coupling admittance between nodes 1 and 2 is 1, therefore times 1, minus node 3 has a voltage 4 upon S, and the admittance of the element connecting nodes 1 and 3 is 1 times 1, minus node 4 has a Laplace transformed voltage 2 upon S, and the admittance between 1 and 4 is 2S, generalized admittance, equals 0. So if you, all the terms here are known except Vc of S. So if you transfer these quantities on the other side and find out an expression for Vc of S, it turns out to be 2 upon S plus 1 over 2s times S plus 1 times 1 minus e to the power of minus S. That is what it will be. So you can write this as 2 upon S and make the partial fraction expansion of this portion only, because later on we will interpret this 1 minus e to the power of minus S, how it reflects in the time domain. So we will make the partial fraction expansion of this only. That will be consisting of 2 terms, half and minus half times 1 minus e to the power of minus S. So essentially therefore you have 3 quantities to deal with. 2 upon S is 1 plus half upon S plus minus half upon S plus 1. That is one group of terms, and the same group of terms multiplied by e to the power of minus S. So if you find the inverse Laplace transform of each one of these groups and add them up, that will be your Vc of t. So Vc of t would be, this will be 2 times ut. Here you have half ut minus e to the power of minus t ut. That is the inverse Laplace transform of this. And you observe that this is the same thing as this, except it is multiplied by e to the power of minus S, which means whatever time function we have here is delayed by 1 second. That's all it means. Therefore this is minus half of u of t minus 1 minus e of minus t minus 1 u of t minus 1. So that is what it would be. You can sketch this Vc of t. So Vc of t would be, this 2 ut will be a step function like this. This is 2 times u of t, and this is ut minus e to the power of minus t ut. So start with it is 0 and exponentially climbs to a value equal to half. So this is half of ut minus e to the power of minus t ut. That is what it will be. As far as this portion is concerned, it has a negative value, it is a negative of this, but it starts from t equals 1. Therefore, it will be something like this and asymptotically reaches half. So if you add all these, you will get some curve comes like this and then it decays to these two will add up to 0 ultimately. So this is your total solution. So that is Vc of t. So this problem illustrates how you can handle the solution when there is a discontinuous time function, and how the discontinuities or a time function is, of course this is discontinuous, and how when finding out the inverse Laplace transform when you have e to the power of minus s or such terms are present, how you can find out the inverse Laplace transform, making use of the property that e to the power of minus s means that that particular function of time is delayed by 1 second. If it is e to the power of minus ts, it is delayed by t second. To discuss the application of Laplace transform technique to a general system, let us consider a system represented by this black box. This is a linear time invariant continuous time system with an input xt and an output yt. We shall assume that all initial conditions are 0. That is, the output response quantity yt and all its derivatives are 0 prior to the application of the input xt. We will also assume that xt is causal. That means x of t is identically 0 for t less than 0. Now, we have taken a single input, single output system, and if there are really a number of inputs, multiple outputs, we can find out the response to each of the individual inputs in turn and use the superposition principle. Therefore, there is no loss of generality involved in our taking a single input, single output system. We have seen that such a linear time invariant continuous time system is in general described by a differential equation of the type an dnx dtn plus an minus 1, the n minus 1 derivative of, this should be y output quantity y, dny dtn, dn minus 1 y dtn minus 1 on up to a naught y equals dmx dtm plus dm minus 1x dtm minus 1. We have a coefficient dm minus 1 here. dm minus 1 x by dtm minus 1 up to b naught x. This is an nth order differential equation with constant coefficients. Now, we assume that yt and all derivatives are 0 for t equals 0 minus and of course t less than 0. That means it's identically the circuit is dead as far as the response quantity is concerned, and so is xt, because xt is a causal function is identically 0 for all negative values of time. So under these assumptions, we can take the Laplace transform of all the terms on the left hand side and right hand side. In doing so, since all the initial conditions are 0, if the Laplace transform of y is y of s, the Laplace transform of dny dtn is simply s to the power of n times y of s. So that makes the transforming this equation a very simple task. So if you take the Laplace transform of that, you have a n s to the power of n plus a n minus 1 s to the power of n minus 1 times a naught plus a naught times y of s equals the Laplace transform of this side of the equation, which is s to the power of m plus a b m minus 1 s to the power of m minus 1 on up to b naught multiplying x of s. So that is the differential equation after transforming its after making the Laplace transform of the differential equation. It is converted into an algebraic equation, transforming relating the transform of the response quantity to the transform of the input quantity. Now the ratio of y of s to x of s is therefore the ratio of two polynomials s to the power of m b m minus 1 s to the power of m minus 1 plus b naught divided by a n s to the power of n a n minus 1 s to the power of n minus 1 c naught. This we can put ratio of two polynomials g of s over f of s. Now I have taken the leading coefficient here to be 1. It doesn't entail any laws of generality, because even if there was a leading coefficient here which is different from 1, we can divide all the terms by that term and make this reduce to 1. Therefore, there is no laws of generality involved in taking this leading coefficient here to be equal to 1. Now this y of s or h of s, x of s in this derived in this fashion is called h of s, the system function. So formally we can say the system function h of s is the Laplace transform of the output quantity y of t by the Laplace transform of the input quantity x of t with 0 initial conditions. What we mean by 0 initial conditions is that the response quantity and all its derivatives are going to be 0 at 0 minus, and the before the application of the input xt. So in this particular case we have taken xt to be a causal function which is identically 0 up to t equals 0 minus, and then until that time the response quantity and all its derivatives are going to be 0. Therefore each of these, when it is transformed into Laplace transform domain, dn y dtn goes as simply s to the power of n times y of s. This system function is also referred to as transfer function in literature, particularly in the context of networks, control systems and so on. This is also referred to as transfer function, another name for this. So essentially when we talk about a system function in the Laplace transform situation like this, we are saying that is the ratio of the Laplace transform of the response quantity to the Laplace transform of the input quantity with 0 initial conditions prior to the application of the input. You recall that earlier we said in the introductory lectures that system function is the ratio of the forced response of the system to the input when the input is at the of an exponential signal. In other words, the earlier definition was h of s was defined as the forced response y of t to an input of the form e to the power of st. So we said at that time that if you had a system for which you have an input est, and then that is xt is equal to this, then the output, the forced response output will be h of s times e to the power of st. Now we have defined the system function in a different way. Are they the same? So we would like to now analyze this and then tie them up and see, we want to show that both of them are indeed the same. Now how do we go about it? We know that x of t from the Laplace transformation theory is related to x of s by 1 over 2 pi j c minus j infinity to c plus j infinity of x of s e power st ds. What it means is, limit as delta omega goes to 0 of summation of elementary signals x of s times delta omega over 2 pi. The x of s is the coefficient density, x of s times delta omega over 2 pi is the coefficient of a signal of this type e power st. Summation over all such signals will yield xt. And how do we take these elementary components? You take the Bromwich contour here and take any particular complex frequency Si and then take a width delta omega, and then if you take the exponential signals corresponding to each such element, that will add up to this. In other words, we can stick right here x Si of t, where Si is one particular frequency and summed up on I. So if this is the situation, then we can think of any arbitrary input xt as the sum of exponential signals of this type. So let us see how it goes. Suppose we have the input and the forced response. So if the input has been e power sit, according to our earlier discussion, the forced response will be hsi e power sit. Now on the other hand, we have now not a single si of t, but a whole lot of these si of t, each weighted by a coefficient like this. Therefore, if I have x si delta omega over 2 pi e power sit, that would give me, by linearity principle, because it's a linear system, you have hsi x of si delta omega over 2 pi e power sit. Now if you, this is one particular complex frequency signal with a tiny amplitude like this. Now we have a whole lot of these complex frequency signals, therefore we take the sum on I, x si delta omega over 2 pi e power sit, that should give me correspondingly limit as delta omega goes to 0 of x si delta omega over 2 pi e power sit. This of course also on limit as delta omega goes to 0. And this is exactly what xt would be. Xt we have seen from the Laplace transform theory is limit delta omega goes to 0 of x si delta omega over 2 pi e power sit. So all these tiny exponential signals ranging from minus infinity to plus infinity along this Bromwich contour, if you add all of them, that will fetch you x of t. That means this is really x of t. So if you have this x of t, and the combination of all such signals can be put in the integral form 1 over 2 pi j c minus j infinity to c plus j infinity of, now s is a running variable, no longer discrete values, x of s times x of s e power st ds, because ds is j times delta omega. So this is what it will be. So from this we have observed, if you take this entire quantity, if you call that yf of t, this yf of t has 1 over 2 pi j c minus j infinity c plus j infinity x of s h of s xs e to the power of st ds. That means the Laplace transform of yf of t will be xs hs times xs. That means we have yf s Laplace transform is Hs times Xs. So according to our earlier definition, we found that the sum of the forced responses will have a Laplace transform which is Hfs times Xfs. But in our Laplace transform theory, we are saying the total response Yfs is equal to Hfs times Xfs. So is it that the total response Yt is the same as Yf of t that we have got obtained here? The answer to this is that they turn out to be the same, because this Laplace transform, inverse Laplace transform integral, provided you take S in the region of convergence of the transform Hfs times Xfs, it turns out from the Laplace transform theory that if you plot Yf of t, this is going to be identically 0 for negative values of time, and it may have some other value like this for t greater than 0. This is Yf of t. So according to the Laplace transform theory, Yf of t is going to be identically 0 for negative values of t, and it will have only values for positive value, non-zero values for only positive values of t. And in our system, we also have Yt, which is identically 0 for negative values of time. Therefore, Yt agrees with Yf of t identically for negative values of time. Therefore, there cannot be any other term if it is introduced that will spoil the initial conditions of the problem. Therefore, this Yf of t is also equal to Yt. Consequently, there cannot be any other extra term that is present. So this Yf of t is indeed equal to Yt. Therefore, Yf of s, which is Hs times Xs, is indeed the same as Ys Xs times Hfs. Therefore, Yf of s obtained in this fashion is the same as Y of t. So the discussion therefore gives us this information that the sum of the forced responses calculated in this manner will also yield the total response. Total response in the sense there cannot be any other term as far as the negative values of time is concerned. But as far as positive t is concerned, this whatever you calculate for Yf of t will include the finite number of transient terms and the finite number of forced frequency terms appropriate to the given Hfs and Xfs. There are finite numbers, and in the conventional sense what we talk about, what we mean by transient terms, transient response and forced response pertaining to xt and ht as far as t greater than or equal to 0 will always be obtained in Yf of t. Even though we are calling this forced response Yf of t includes the transients and the steady state responses that emanate from t equals 0 onwards. The reason why we are saying this forced response, because all these tiny exponentials here start from minus infinity onwards. So they're all starting from minus infinity. All these exponentials are starting, and each of them produce a forced response, and the sum of those forced responses agrees with the total solution for negative values of time. That means there cannot be any other additional terms starting from t equals minus infinity onwards. But Yf of t, which is obtained here, as far as this part of the solution is concerned, it includes both the transient and steady state terms, which we talk about in a conventional fashion. So Hfs that was defined earlier and Hfs that we have defined now are one and the same. Therefore, we don't have to make any distinction between these two. And this Hfs plays a very important role in system studies. It has got various useful properties and various interesting properties, and it will be our task now to take up a discussion of the various important aspects of the system function Hfs, and that we will take up next. So the system function Hfs has many important connotations. So it will be our task now to look at these connotations. So let us say this, it has many facets to this system function Hfs, and that's what we would like to study. So we are talking about a linear, time invariant, continuous time system with an input xt and an output yt, and the system function enables us to relate the output to the input not by means of a differential equation, which is complicated, but by a simple algebraic equation in the Laplace transform domain. We also assume here that 0 initial conditions. That is important. So once we have the 0 initial conditions, the output and input are related by a pure algebraic equation where HFS is in general a rational function, a ratio of two polynomials. And that differential equation is converted to an algebraic equation of this type is the central advantage of the transform technique, of which Laplace transform is a very prominent technique. Now let us look at the various aspects. A. Suppose we have impulse input. A special case, not a general x of t, but let us say we have an impulse input. So what we are talking about here is input is delta t, and you get an output which perhaps varies like this. We will call that h of t. So corresponding to an impulse input, impulse at the origin, you get an output h of t. H of t is called the impulse response, which already we observed earlier. Now applying this formula here, YFS, whatever output you get here is related to the input by this manner HFS, the system function, times XFS. XFS happens to be 1 because xt happens to be delta t, XFS has 1. The Laplace transform of delta t, as we know, equals 1. So that means the output is simply HFS, but that output we are calling h of t. Therefore, Laplace transform, or I will write this YFS itself is HFS. So the inverse Laplace transform of YFS, which in our particular case is h of t, is the inverse Laplace transform of HFS. In other words, the impulse response ht and the system function form a Laplace transform pair. And it is in anticipation of that we use the symbol h for the impulse response and capital H for the system function. So this is a very important result. The system function HFS is the Laplace transform of a impulse response. That means you apply a unit impulse to the system with 0 initial conditions, unit impulse stationed at t equals 0. Whatever response you get, we call that h of t. That will be the inverse Laplace transform of HFS. Or if you know impulse response h of t, you can find out HFS by taking the Laplace transform of ht. These two form a Laplace transform pair. Now using this information, general solution in time domain, general input xt, suppose you are having, and you want to find out the output in time domain, we know that YFS equals HFS times XSFS. Now by the convolution property, we know if YFS is the product of two quantities HFS and XFS, then YT we know is the convolution of the time domain quantities which are the inverse Laplace transforms of these two. The inverse Laplace transform of HFS is HT. The inverse Laplace transform of XFS is your XT. So in other words, the output is the convolution of the impulse response and the input quantity, which a fact which you have already observed in our preliminary discussion. We already noted this. I am just trying to relate this to the Laplace transform equation in this manner. What does it mean? This is the convolution integral. It means 0 to t h of t minus tau x tau d tau. Alternately, if you wish, you can write as 0 to t h tau x of t minus tau d tau. These are, because this you can interchange the roles of these, both these are equivalent to each other. And as I mentioned earlier on, if it may turn out that x of t may have impulses at the origin, h of t may have impulses at the origin. So to take care of those impulses at the origin, in general it would be advisable to take the 0 minus to t plus, 0 minus to t plus, if to take care of the possibility that xt or ht may have impulses at the origin. If they don't have impulses at the origin, it doesn't matter whether you take 0 to t or 0 plus or 0 minus. Now these integrals are called convolution integrals. They are also called in literature superposition integrals, because after all you are superposing the effect of x of t by treating them as a variety of, as a summation of different impulses, something which we already discussed. So the significance of this convolution integral as a superposition of the input considered as a sum of impulses is something which we have already discussed. A third aspect, I also mentioned in our earlier discussion that step response is also a way of characterizing a linear system. So let us see how it is related to your system function HFS. So in step response, we are thinking of a unit step applied as the input. So xt is ut, and the corresponding output, whatever you are having here, is given a special symbol at. And this at is called the step response. Sometimes it is called indicial response. Now using this general equation, ys equals hs times x of s. So in our particular case, this hfs and x of s happens to be 1 over s, because the Laplace transform of a unit step is 1 over s. And y of s, the particular Laplace transform of the step response that we are getting, let us call that a of s. That means if at has for its Laplace transform a of s, capital A of s, then a of s is hs times 1 over s, or h of s equals s times a of s. So the relation between Laplace transform of the step response and the Laplace transform of the impulse response is given like this: h of s times 1 over s is a of s, or s times h is equal to h of s.